All right, let's take a look at an exercise involving conservation of momentum, conservation of linear momentum. So we have two figure skaters here with different weights given, and they push off of each other, and some information is given about one of them, the speed of one of them after they push off. So in conservation of momentum problems, we generally use it during a collision, right? And so there's kind of like before the collision and after the collision. So it's best to start out with drawing two pictures, essentially two, not quite free body diagrams, but two sketches of what it looks like before and after. And so let's have like our initial condition here, which is really like before this pushing off, and then we'll have a final condition over here. This is like after, and we had the two figure skaters. I'll just call them A and B, something like this. So they're different sizes, different masses there. And then after we have here's figure skater A, and here's figure skater B. And now we know something about the heavier skater. I'll say B is the heavier one. So let's just call maybe this is A, figure skater A. This is figure skater B. And we know the heavier one moves this way at 1.5. Well, actually just moves at 1.5 meters per second. I'll arbitrarily choose off to the right. And it seems that they were maybe at rest first, right? So our speed here, speed of both of them are equal to 0. So this is basically information that we have given to us. Now, when we set up these two sketches before and after, this one on the left, this before, is just any time before, and then the one on the right after is immediately after. So we think of essentially the time that passes, this delta t that passes between the initial condition and the final condition, is essentially equal to 0, right? It's not actually completely equal to 0, but it's basically equal to 0. And this is what allows us to use the conservation of momentum in the first place, is that we assume that this happens instantaneously, effectively. So so we have this this happens, well, there's a couple ways. Either there are no net external forces, or it happens over an infinitely small time, in which case actually they tell us a frictionless ice. So we have both of these things being true, but in generally we look at this time interval to be equal to 0. So it's immediately before and immediately after. So just kind of writing out some of this information we have given to us. We're given the weights of these, right? So we know, well, I won't put that in the figure here just to save some room, but we're given the weights of both of those. The initial velocity of both of them are equal to 0. So this is like VA is equal to 0 and VB is equal to 0, and this is going to be equal to VB final, and VA final is going to be something we don't really know, right? So VA final equals question mark, and really it could go to the right or to the left, but just based on our experience, it's most likely going to go back to the left. This is what we call recoil. So the way that we use conservation of momentum, then, so it says that if it's collision, and this is essentially a collision, it's more like an explosion, I guess, because the two are pushing off from each other, but you think of an explosion just like a collision. Same fundamentals there. So the way that we use this conservation of momentum in a collision, we say that if momentum is conserved, then the initial momentum of the system is equal to, let me actually go ahead and write system. So the initial momentum of the entire system is equal to the final momentum of the entire system. It's important that it's the entire system that we're considering. It's not just like the momentum of A initial equals the momentum of A final. That doesn't work. But the momentum of the entire system is the same both before the collision and after the collision, right? So the momentum over here The initial momentum has to equal the final momentum. And so then to find the momentum of the system, well, that's just the sum of the individual momentums, right? And so, for the initial condition, we have the initial momentum of, well, I'll call it PA, the momentum of skater A, plus the momentum of skater B initially, is equal to the momentum of skater A plus the momentum of skater B final. And these are vectors. Remember, momentum is a vector, so it has to be the vector sum of them. Right, so then, expanding on momentum, we have, this will be the mass of A times the velocity of A plus mass of B times velocity of B. And the initial condition is equal to the mass of A times the velocity of A plus the mass of B times the velocity of B. And the final condition, right? Or before and after. Of course, we knew something about the initial velocity, right? The initial velocity of both of them were 0. And so that makes life pretty easy, that this is 0 and this is 0. So the initial momentum is equal to 0. Right? So then the final momentum will also be equal to 0. So we have here, this is 0 is equal to the mass of A times the velocity of A plus mass of B times velocity of B in the final condition. Now you might think, well, how is that possible that the momentum is 0 when they're clearly moving? Well, you have to remember here that the momentum is a vector. So this can be, we're looking at one-dimensional motion, right? It's moving in the positive and negative x directions. One of these can be positive, one of them can be negative, so that they add up to 0, right? So things can still be moving, but the total momentum equal to 0, right? But they have to be moving in opposite directions, which is intuitively what we thought anyway. This one is moving off to the right, which I can call positive direction. I should really have given a coordinate system earlier. So there's a coordinate system we're using. So this will have a positive velocity, so a positive momentum, and this will have a negative velocity, so a negative momentum, and they'll add up to 0. So solving this and plugging in, we knew what VB final, based on our coordinate system. I wasn't actually able to plug in a value of this until I chose a coordinate system. It just told us that it moved off at a speed of 1.5 meters per second. Whether or not that's positive or negative depends on my coordinate system. So I had to establish this first. Right? So I still need coordinate systems for momentum. And so solving this, let's go ahead and plug things in. We have 0 is equal to the mass of A times velocity of A, which I'm not sure what this is, and that's final. I'll just distribute this final into these, plus the mass of B times 1.5. So I can solve for the velocity of A. The final velocity of A is going to be equal to, this will be the mass of B, so negative mass of B times 1.5 divided by the mass of A. And the masses, we were actually given weights, right? This is 625 is equal to the mass of A times gravity, and the 725 is the mass of B times gravity, right? So we have the mass, then like mass of A is going to be 625 divided by G, and the mass of B is 725 divided by G. And so plugging this in, we have, I guess we'll finish this up. So VA final is going to be negative 725 over G times 1.5 divided by 625 over G. These G's actually end up canceling anyway. And we end up here with the final velocity of A is equal to negative 1.74 meters per second. And then we need to go back and kind of just think about this a little bit. So negative 1.74 meters per second. Does that make sense? Well, we look at just fundamentally what's going on here, that B was moving off at 1.5 meters per second to the right, as I have it defined. So then A needs to move off to the left. So that's good. So our sign is good. So the fact that we have a negative here, this is good. Now let's look at just kind of the relative magnitude of these as well. So 1.74, that means it's going to be moving faster than B was, which actually also makes sense because B is heavier than A, right? So to have, the same magnitude of momentum, but in the opposite direction, it needs to be moving faster, right? So it makes sense that it's a little bit faster than B. So this all makes sense, and we feel good about this, right? So that takes care of the answer for part A. Now part B asks, let's just clean this up a little bit. Part B is asking how much kinetic energy is created during this, and where does the energy come from? So we know that energy isn't really created. This is why it's in quotations here, right? So energy isn't really created. It just simply changes form. So this is why it asks for where does it come from. It's not really created. It comes from somewhere else. We can talk about where it comes from now, I guess. It comes from, essentially you have energy in the muscles of the skaters, right? That is, I guess, chemical energy, or food energy from the very beginning. And that energy in the muscles is then turned into kinetic energy. But let's look at how much kinetic energy is created. And so for part B, this change in kinetic energy, this would be equal to our final kinetic energy minus the initial kinetic energy, right? And so these kinetic energies are going to be the kinetic energies of the whole system. So this is going to be like our final kinetic energy. This is going to be the kinetic energy of skater A, final, plus the kinetic energy of skater B, final, right? And the same would be true about the initial kinetic energy, but I'm not going to write that out because neither one of them were moving at the first place, right? So they had zero kinetic energy, because kinetic energy is 1/2 mass times speed squared. And so since neither one was moving, the initial kinetic energy was equal to 0. Right? So this means that this change in kinetic energy, or this creation of kinetic energy, I should say conversion of kinetic energy, or to kinetic energy, this is just going to be equal to the final kinetic energy of the system. And so then that is, the kinetic energy of A final plus B final. And so that's 1/2 mass of A times the final velocity of A squared, right? Because kinetic energy is 1/2 mv squared, plus 1/2 mass of B times the final velocity of B squared, right? So we can just calculate this out, and they have different masses and different velocities, right? So we have to plug in each of these. And note here too that the kinetic energy has the speed squared, right? And so kinetic energy is always positive. It's not a vector quantity. So their kinetic energies will combine. Their momentums actually subtracted, right? So they had the same magnitude of momentum, opposite directions, so that the total momentum of the system was 0 after the collision. But the kinetic energy doesn't work out that way. The total kinetic energy is the sum of individual kinetic energies. So the more parts you have moving, regardless of direction, the more kinetic energy you have. Later on, we'll expand on this into like kinetic theory of gases. As they get hotter and they have more energy, they move faster, but they're moving all random directions. And then we'll talk about how temperature is actually just an average of kinetic energy. But that's later. So we have this change in kinetic energy. This is going to be 1/2. The mass of A was 625 over g, times the speed of A, which was this 1.74. I'll put in a negative just for completeness, I guess. Negative 1.74 squared plus 1/2 of 725 over g times this one was moving at 1.5 meters per second. And we have the change in kinetic energy, or the conversion of kinetic energy. This comes out to 179.8 joules. So 179.8 joules of muscle energy converted to kinetic energy.